Hi, my name is Connor Gatlin, and my team members are Fan Gayo and Ruisi Wang, and our final project is called Stock Performance Predictions based on news analytics. So some of the motivation behind this project was to understand the predictive power of news. Historically, we know that news and stock performance are highly correlated. They go hand in hand, and when news is up or down, stock market and stock prices can go up or down. So the goal of this project is to compare stock performance predictive models based on news data and market data. For this project, we used two different data sets for modeling. Both of these data sets span from 2007 to the present and contain information on most US stocks. The first data set contains financial market data from Intrinio and contains about 4 million samples. This stock market data includes info like asset code, open and close stock price, and trading volume. It also contains a variety of returns calculated over different time spans. These are usually backwards looking in time and are either raw or market residualized. This data also contains a 10-day leading return that is forward looking and market residualized. This is going to be our label for training and the piece of data that we will be attempting to predict in our models. The second dataset contains news articles and alerts published about assets dating back to 2007. It has around 9.3 million samples and is around 4.7 gigabytes. This data is provided by Thomson Reuters and contains info like headline, asset code mentions, market commentary, and a general sentiment score for the article. Some of the major tools that we've used for this project are Python, scikit-learn, Node.js, D3.js, PyPlot, Jupyter Notebook, and Google Cloud. So before we did any modeling, we wanted to visualize the data. And to do this, we created a Node.js-based website that includes D3.js for some market visualization as well as news analytics visualization. I'm going to give you a brief demo of that, and so we're going to go over that right now. So this is our web page, and what you can do is enter a stock ticker or asset code and click Analyze. And what this is going to do is it's going to search through the data set that we have provided and show the market analysis and news headlines for that specific asset. So this takes about 30 seconds, so I'm going to fast forward this video so you can see. So the website is now loaded with the stock and news data. So on the left, you'll see a market analysis chart. What this shows is the close price of this specific stock, which is Apple, as well as the 10-day and 50-day moving averages. Below that, you'll see a volume chart, and below that, an RSI and MACD analysis chart for this specific stock over the time period. You can zoom into this stock and zoom out to get more detail, and we use this to look for outliers when we were doing our data exploration. On the right, you can see news headlines, so I can scroll and see the sentiment, either positive, negative, or neutral, the date that it was posted, and the headline of that specific news article. So along with the website visualization, we also perform data exploration through other charts and graphs, some of which are displayed on this slide. This was to help us get a better feel for what the data contained, if there were any outliers, and what data we needed to clip in order to fix those outliers. So the top will show some of the news data examples, and the bottom will show some of the charts that we came up with for the market data. And the bottom right one is important because this is a plot of the mean market leading return. This is one of the charts that was very indicative of large outliers, which we wanted to get rid of before training our models, and I'll show you that on the next slide. As I mentioned previously, the market leading return graph indicated a few outliers that may affect our model. So to clean this up, we clipped any market data that had a future market return greater than 2 standard deviations off the mean. The result of this was a much more even distribution of returns as shown on the top right graph. We also noticed in data exploration that most of the top one-day price changes occurred in 2010. To us, this didn't make sense because nothing dramatic happened in 2010 in the stock market. We actually found that the price of one stock fell by $10,000 in one day. So when we looked further, we found about 16 other outliers like this and remove those invalid data points. The bottom right chart shows the results, which make a lot more sense. After cleaning the data, we worked on extracting features for our models and merging the news and market data. For the market data, we extracted a number of new features, for example, close to open ratio and volume to average volume ratio. We also encoded all the categorical features like asset code and asset name so that they could be used in a non-categorical model. For the news data, we converted headlines and subjects to a vector representation using a TF-IDF transformer. We also encoded the other categorical features and flattened the news articles to 1 row per day per asset code. To do this, we had to calculate the mean, min, max, and standard deviation of some of these features over each article in a given day. Then, when we did that, we were able to merge the news and market data sets on the day and asset code features. So in total, the combined data set had 4 million samples and 114 features per sample. For our modeling, we decided to use a special score function in order to evaluate and compare each of the models. Each of the models will produce this value between -1 and 1, representing how confident it is that a specific stock will have a positive return over the next 10 days. So if a model is 100% confident, then a stock will outperform the market over the next 10 days. The score will be a 1. Then, using this confidence value, we calculate a score for each day, and then ultimately the final score for the model is calculated as the mean of the scores for each day in the test set divided by the standard deviation of the scores. So after the evaluation was created and the data set was ready, we decided on 3 models and a benchmark model to train the data on. First, we created a simple benchmark model that we could compare against. This basically consists of giving every asset a confidence value of 1. Then we decided to train 1 classifier, 1 regression model, and 1 neural network. For the classifier, we use the CatBoost model. This is a gradient-boosted decision tree classifier that excels with categorical data. Even though we converted all categorical data, we still decided on the CatBoost model because of its proven speed and efficiency with large data sets. For the regression model, we used LightGBM. This also uses gradient-boosted decision trees and implements gradient-based one-side sampling for efficiency and scalability. And for the last model, we decided on a long short-term memory neural network. LSTM is a recurrent neural network and is well suited for classifying based on time series data, which is why we thought it would be a good fit. As discussed before, the output of these models is a predicted confidence as shown in the graph on the right. We split our data set into 70% training data, 20% validation data, and 10% test data. All 3 models that we used required extensive hyperparameter tuning to ensure that we didn't overfit to the training data, so the validation data set was used in this hyperparameter tuning. You can see the scores that were calculated on the test data for each of the models in the bottom table. As expected, the benchmark model scored very low at 0.016. We ran the CatBoost classifier with and without the news data added. With just market data, the classifier scored 0.630, but with news data added on top of the market data, the classifier improved to 0.850. The LightGBM regressor performed a little bit better than the CatBoost classifier, scoring 0.916, and the LSTM neural network is currently still being run on the entire data set. So for the LSTM score, please refer to our paper. So the big takeaways from these results are that 1, the LightGBM regressor provided the best score on the test set. 2, all models provided significant improvement over the benchmark score. And 3, we saw a 34.9% improvement when news data was added to the classification model. We believe that from this data, we can make the conclusion that past stock performance can be a good predictor of future performance, but the addition of sentiment analysis, news stories, and headlines can create an even stronger predictor. The chart here shows stock data from a randomly selected company in the test data set. Above is the closing price plot, and below is a buy and sell signal plot produced by our classification model. As discussed on the previous slide, these buy and sell signals are over 85% accurate with the cat boost model and 91% accurate with the light GBN model.